Hello to everyone. My name is Bhagyashri Thurat and I am going to present a video lecture on series resonance part 2. Already part 1 is uploaded. So before listening this lecture, it is essential that you have to listen part 1 lecture. In part 1, we studied what is resonance condition, types of resonance, electrical resonance circuit, RLC circuit, series RLC circuit, then quality factor importance, derivation for resonant frequency, and one solved example. In second part, we are going to study quality factor, how it is related to voltage across inductor, voltage across capacitor, VL and VC at resonance, how to solve examples on quality factor, what is selectivity, selectivity graph, and solved examples on entire series resonance topic. In the first lecture, we also have a formula for quality factor. We also study the formula for quality factor. So by definition, QS is equal to reactive power divided by average power in circuit. So in our in RLC series circuit, the reactive power is having, for reactive power there are two components. First is an inductor and second one is a capacitor. So for inductor, quality factor at resonance is equal to, formula for power is a current square I square into impedance. So here I square and impedance is nothing but reactance of inductor XL divided by I square into average power. So for average power we are calculating QS. QS means resonance condition quality factor. So at resonance condition, total impedance is equal to R. So quality factor at resonance for inductor is equal to I square into reactance of inductor XL divided by I square into R. So quality factor is equal to XL divided by R, because I square get cancelled here. XL is nothing but frequency in radians omega s into value of an inductor divided by R. This R, if this R resistance is just a resistance of coil, that means the voltage source we are using for series RLC circuit is ideal. The ideal voltage source internal resistance is 0. At that time, quality factor at resonance is equal to, quality factor of a coil is denoted as Q suffix small l is equal to XL, reactance of inductor, and this R is going to become your internal resistance of coil. If that means this total impedance of resistor is equal to RL, internal resistance of coil, because internal resistance of source is 0. So quality factor at resonance is equal to omega s into L divided by R. Omega s is nothing but 2 pi Fs, resonance frequency in Hertz, into L divided by R. so is equal to 2 pi r, and Fs in the first part of video lecture we derive a derivation that Fs resonant frequency in Hertz is equal to 1 divided by 2 pi under root of Lc into L. So 2 pi get cancelled. So L divided by R into 1 divided by under root of Lc. Under root of Lc is get cancelled, and the quality factor at resonance is equal to 1 divided by R under root of inductor value divided by capacitor value. From this answer, we can conclude that quality factor at resonance is actually depend on resistance value, inductor value and capacitor value in series resonance circuit, and it is not depend on applied voltage. That means if applied voltage is changed, your quality factor is not going to change with respect to applied voltage. If you want to change quality factor in circuit, then you must have to change resistor, inductor or capacitor. And this is the derivation for quality factor at resonance in terms of circuit parameters. Now, voltage across inductor. General formula is XL, reactance of inductor, into current. Current is equal to applied voltage divided by total impedance in circuit. So XL, VL is equal to XL into applied voltage E divided by ZT. At resonance, ZT is equal to R. XL is as it is, and applied voltage E is also as it is. So at resonance, quality factor at resonance into E is equal to voltage across inductor. Similarly, voltage across capacitor, similarly we can have formula is Xc into I. So it is equal to Xc, I is equal to applied voltage divided by total impedance. At resonance, impedance is R. So Xc into applied voltage E divided by R is equal to quality factor at resonance into applied voltage. So VL and VC at resonance is equal, both are equal, and the answer is quality factor at resonance into applied voltage. Usually for communication system, quality factor is greater than 1. Then in such conditions, voltage across inductor, voltage across capacitor of series resonance circuit is always greater than input voltage, input applied voltage. Or in other words, this series resonance circuit is also called as voltage magnifier circuit, because voltage across inductor and voltage across capacitor at resonance is magnified by quality factor. Example, if quality factor is 5 and applied voltage is a 10, then at resonance the voltage across capacitor and inductor is a 50 volt. One example, how to calculate quality factor. This is a simple RLC series circuit. Applied voltage is a 10 volt, 0 degree phase shift. Resistor is a 6 ohm. XL is 480 ohm. XC is a 480 ohm. That means this is a resonance condition. So no need to calculate frequency. So quality factor formula is XL divided by R. XL is a 480 ohm divided by 6 ohm. We already studied quality factor is a dimensionless quantity. So ohm get cancelled. Your answer is 80. Now voltage across inductor, voltage across capacitor at resonance is quality factor into applied voltage. Last slide we have a derivation. So it is equal to 80 into applied voltage 10 volt. So at resonance, voltage across inductor, voltage across capacitor is 800 volt. That means if circuit is in state of resonance, the VL and VC, voltage across inductor and voltage across capacitor of series resonance circuit is greater than input voltage if quality factor is greater than 1. If we plot the graph for frequency versus current in a series resonance circuit, frequency is on y-axis and current is on frequency is on x-axis and current is on y-axis. Then at zero frequency, zero current is present. As frequency increases, current is increases till resonant frequency, because at resonance frequency the impedance is minimum, and after resonance frequency the current is decreases sharply. The definite range of frequency at which I near its maximum value, Z is minimum. This called as half power frequency. These are the definite frequency and it is F1 and F2. If you observe this graph from 0 to Fs, graph is gradually increases because Zt is a R plus J XL minus XC square. So at low frequency, capacitive impedance is very low, but inductive impedance is high. So XL is equal to 2 pi FL. So 2 pi L is a constant and frequency is gradually increases. So that's why from F1 to Fs, this graph is gradually increases. That's why the circuit is inductive. After Fs, circuit becomes capacitive. Capacitive impedance is 1 divided by 2 pi Fc. So because of this capacitive impedance, after resonant frequency, current is sharply decreases. So always remember, at Fs, F1 and F2 both are not symmetrical, and F2 minus F1 is known as a bandwidth of series resonant circuit. Now we know that for power, formula is I square into R. So maximum power is equal to I square max into R, because R is a constant factor. Impedance is always constant for any circuit when the circuit is designed. After designing, the resistor is not changes its value for depend on current or voltages. So I max is equal to I square RMS value. So RMS value is equal to 1 divided by under root of 2 I max. 1 divided by under root of 2 is equal to 0.707 I max square into R. 0.707 square is equal to 0.5. So this equal to 1 divided by 2 P max. So that's why at F1 and F2 the half power we are calculated, and that's why F1 and F2 is called as half power frequency. So there are some solved examples on series resonance. For series resonant circuit, R is a 2 ohm, XL is a 10 ohm, XC is equal to 10 ohm with applied voltage. That means this is a resonance condition. Question is, what is quality factor of circuit at resonance? Find voltage across inductor, voltage across capacitor at resonance. For quality factor, formula is XL divided by R. So XL is 10 ohm and R is a 2 ohm. So quality factor is equal to 5. Voltage across inductor is equal to current into XL with phase shift 90 degree, because inductor is having a 90 degree phase shift. It is equal to 50 volt angle 90 degree. For current at resonance condition, formula is applied voltage divided by resistor value. So it is 10 divided by 2 is equal to 5 ampere. Now for VC, formula current into reactance of inductor and reactance of capacitor, and the phase shift is minus 90 degree. So 50 volt minus 90 degree. That means voltage value is the same, but there is a phase shift of a minus 90 degree. Now repeat the above example for capacitor 0.1 microfarad, inductor 1 millihenry and resistor 100 ohm. For solve this example as a homework. Hint is step 1, calculate resonant frequency using formula Fs is equal to 1 divided by 2 pi under root of LC. Then calculate XL at resonance. For XL at resonance, XL is equal to 2 pi Fs into L divided by R. And last, calculate quality factor. For quality factor, calculate quality factor is equal to XL divided by R. Hence, we completed our entire unit on series resonance circuit. If you want to simulate series resonance circuit, in the next lecture, I am going to show you the simulation of series resonance circuit on multisim platform. So if you want to cross check or compare the theoretical value and practically simulated value, then please listen next lecture on series resonance simulation using multisim platform. Thank you.